Good afternoon and welcome back to Dr. Logic Awkwardly Does Logic. Last video, I gave you the basic axioms for the modal system K. In this video, I'm going to give you the three primitive transformation rules. Two of them are not modal specific. I don't want to say purely propositional because they're actually rules that you'll find in predicate logic systems, for instance, but they are entirely non-modal, and one of them is modal. All of them are fairly straightforward, though one of them might require a couple of examples just to illustrate how it works. So the first one is the easiest one. It's the rule of modus ponens. This one says that if you have a theorem phi and you have another theorem phi implies psi, then psi is also a theorem. So you've got a conditional, you've got its antecedent, you've already proven them, you've already written them down in your list of proofs. You can also get the consequence of the conditional. So just writing this out in English so that you've got another way of thinking about it. If phi is a theorem and phi implies psi is a theorem, then psi is also a theorem. So the way you can think about this is that any system that contains modus ponens is closed under implication. So you would never have an example of a conditional where you have the antecedent, but you don't also have the consequent. So that's our first rule. And as you can see, it says nothing whatsoever about modality. The second rule is the rule of uniform substitution. So I will say it out loud and then write down a definition of it. Uniform substitution says that the result of uniformly, i.e. across the entire formula, replacing atoms P1 to Pn by well-formed formulas of any complexity, beta 1 to beta n, in something that is already a theorem will also be a theorem. So the result of uniformly replacing atoms P1 up to Pn with well-formed formulas beta 1 up to beta n in a theorem is also a theorem. So if you take a theorem and wherever you find an instance of a particular atom, you replace it with another formula, then the result that you have is also a theorem. So there are a couple of different ways that we can write kind of this process of doing the substitution. So suppose that we have a formula phi. We can either say that if we take all of the beta 1 to beta n and substitute them in for the P1 to Pn, we can write it like this. So we have kind of all of the formulas we're substituting in, all of the ones that we're substituting out. Or we can also write it another way where you do kind of each substitution. So beta 1 gets substituted for P1 all the way up to beta n gets substituted for Pn. So both of these are two different ways of writing the same thing. Two ways of writing the same thing. Which one you use just depends on how many substitutions you're doing at the same time, and also kind of what you want to draw your attention to. So here's just a very brief proof. Remember that we have our axiom, the K axiom, necessarily, if necessarily P implies Q, then necessarily P implies necessarily Q. We can write this down as the first line of our proof because it is an axiom. And then I can go and I can change all of the P's to R's. So the result of doing uniform substitution, substituting R in for P, gets me this. So the way you would annotate this is just uniform substitution. You're doing it on line 1. and wherever you have P, you put R. But I can also substitute in something more complex. So for instance, this is also a theorem that I can write down. P implies P and Q, and necessarily P implies necessarily P and Q. So here, this is an instance of uniform substitution, again, on line 1, where I am substituting in P and Q for the single atom Q. The two things to remember with the uniform substitution, these are the two things you have to check every time you apply it, because these are the things that people often forget. And if you don't forget to check these two things are the case, you will end up applying the rule wrong. First, you can only substitute in for atoms. So I can change this P and this Q and this R and this P and this Q. But for instance, I couldn't take this entire formula and substitute it out. I can substitute it in, but I can't substitute it out. Once I have that, then this P and this P are, they are the same atoms. So any substitution would have to happen at the level of the atoms. So that's the first one. The other is you must substitute all instances of the atom that you're substituting out. So you can't, for instance, over here, I couldn't decide just to substitute out this P and change it for R and then leave it here. That isn't uniform anymore. So uniform substitution, you must substitute all of the occurrences of the atom, and you can only substitute out atoms. If you remember these two things, you won't have any problem with this rule. And then rule number 3 is the purely modal rule. This is the rule of necessitation. It says if some formula phi is a theorem, then necessary phi is a theorem. So the idea is that anytime that you've already proven something, you can always stick a box on the front. And this is very useful because this is the only way so far, other than the K axiom, that we can actually get modalities into the formulas in our proof. Without some way of kind of getting structure beyond the structure that is already in the K axiom, it would be very hard to do anything interesting. So if you can prove something is a theorem, then you can also prove that formula with a box on the front. Here are the 3 rules for basic normal modal propositional logics. Now, I said a while back that I would tell you what it means for a logic to be normal. And basically what it just means is this is a logic that is built on system K. So a normal modal logic is any logic that contains axiom K and has as rules uniform substitution, modus ponens, and we often just write necessitation by N or by neg. You don't have to write the whole rule out. So system K is a normal modal logic, and every logic that we build extending this system will also be normal. At this point, we are now going to be in a position where we could start proving things. We're not going to do that quite yet, because first I want to say something about why these rules. Why these rules? Why this axiom? Why is this what we are taking as our foundation? So we will specifically be interested in questions of, like, are these rules, in a sense, good rules? Now, you probably already believe modus ponens is. I've given you proofs of the soundness of modus ponens, but we do need to show in the context of our particular semantics, the Kripke frames, that these are still good rules. So that's what we'll do next. and then we will get to a point where we start actually proving things. So take care, join me then, see you in a bit. Cheers.